Hi, I'm Isaiah with Web Brass and Glass, and today I'm going to be doing a part 2 video follow-up about the SEG roller. Numerous things I want to show you, the viewer who's watching, and not just go through a bunch of images this time, but actually showing oscilloscope readouts, eddy current, rotation, resonance chamber I'm working on to show off the vibration, and a few other things with magnetizing. I'm very excited about this one, so stay tuned, and we're going to launch into this about the rollers. All right, so I wanted to kind of circle back around from the prior video. I showed the copper stator, well, and how it will make the roller rings rotate when they are brought near, and so most of the rings I've been working with won't do it. I spent a couple weeks ago quite a long time doing a whole bunch of different magnetizing tests, and finally at the end of the day discovered the way to modify the magnetic field so it will induce rotation on the roller's ring magnet. And while doing that, I discovered another cool thing using these little guys, and I'll zoom in here to show how they work in relation to this. All right, turn this on. Ooh, we're feeling peppy today, 915 RPM. Okay, so I got two of these guys. There we go. Two of these guys off of Amazon, and they're a tiny little magnet supported by this kind of gimbal structure. So it's a magnetic pole finder, manual, not electronic. But one of the cool things I found in relation to this is it spins in relation to the copper stator quite fast. The camera doesn't do it justice, but it's going quite well, very fast. And I don't even touch it. There we go. It doesn't need to touch. Pretty cool. All right, and the next, this is one of the rings that I magnetized back in the summer of last year, and it took me an entire day to rediscover how in the world I accidentally did this one that oscillates or rotates when this is moving. Now, fortunately, I was able to do 4 more rings perfectly and match the symmetry, match the magnetic field, and we're going to take a look here pretty quick at the oscilloscope readings on this one compared to others with different points and things. But I want to show you all again how this acts in relation to the stator. And it's either direction, of course. There we go. It's a very particular type of field to get this to work right. But it does oscillate. Now I've tried, let's try another one. And this magnet will be with 17 points. And a copper jack on it. It doesn't really do anything. Yeah. Come on. Yep, nothing. But we'll take a look at the oscilloscope readings anyway. And here's one with 33 points and 1 empty. 1 null, I should say. 33 points, 1 null. Now this is probably just going to oscillate because, yeah, there we go. The mechanical oscillation in the ring magnet itself causes it to rotate. But let's try a different experiment. Let's actually put this one on a bearing and see if we can get it to spin. Put the 33 points and 1 empty point, or 33 points, 1 null, onto this better bearing. Oh, interesting, it does work. Maybe, does it work? Come on. Maybe a certain speed. I need to build a mount for this. Yeah, this doesn't work. So I'm not too surprised because the geometry of this is not right. It's not just putting points. You actually need to put a wave field onto this, which the oscillating ring has. Now let's take a look at the oscilloscope readings of these ring magnets. So I'm going to go through with these ring magnets one by one, showing a standard normal magnet that has no unique field. It doesn't have any waveforms. It's just standard, industry standard. So this little gizmo here, this is where the ring magnet is mounted onto this. There's a Gauss meter probe that connects into the FW Bell Gauss meter, Tesla Gauss meter. This connects into the oscilloscope, and you're able to see a digital readout of the ring magnet as it rotates. Pretty awesome. So let's begin with just a normal ring magnet. All right, so this is the normal ring magnet. Nothing I have done, it's industry standard. I'm gonna put it on this guy, mount the security holder. The oscilloscope, the Gauss meter are on. Now I have these cool compasses here. So this is the axis direction. This is the horizontal direction of the ring to monitor any kind of impressions the waveforms will make. Come on, tripod, there we go. All right, so you all can see. You can see. All right, switch this sucker on. And you'll start to see here pretty much not a perfectly flat line, but an industry standard line as this ring is rotating. The compasses are not moving at all, as they shouldn't be, because it's basically... Now it's not a perfectly flat line. There's little imperfections in the magnetic field you'll see going through here, even though this is an industry standard magnet. Slap bang with the capacitor box. We'll zoom out a little bit to 1 volt, and it gets even flatter. Not very impressive, right? Okay. This is the Gauss meter I'm using. I got 2 of them now, so I'm gonna be hooking up eventually down the road, reworking this system to have 2 Gauss meters, 2 inputs, 2 channels basically, so you can have a double direction of seeing the fields. So anyway, that's coming up. So let's move on to a magnet that I have that has 17 points and see what that looks like. 17 points. It has a copper jacket on it, so it might distort some of the readings, but we'll see. You can see the readout on the oscilloscope as it rotates. It's only doing 6 RPM, pretty slow. Nice. So there, 17 points per rotation, and then I believe 1 section is null, and then it goes back to 17. So basically this is your rotation. Let's see if we can zoom in here a little bit. There we go. So I left like 1 point empty, 17 points and 1 null. That's 1 rotation. One, I can zoom in. Some people might be interested to see these waveforms. Very clean for these waveforms with the magnetizing module I'm using, except for that point here is intended. But pretty clean lines. So So again, this is 17 point, and those fields are going right through that copper as if it wasn't there. Now, is there any deflection in the compasses? Let's see. Nothing. I don't see any movement. And it could be they're just too far away. Some of these magnets I've measured that the change goes out almost 4 inches. Of course, this doesn't want to stay. What in the world? Yeah, whatever. This jig needs to be worked on. Let's see if it does anything here. Sometimes they'll just wobble them, depending on the ring magnet. A lot of this work is just kind of slow, monotonous work. Testing, retesting, finding out what works and what doesn't. Okay, so let's move on. This hasn't changed a bit. Now here's a magnet. I put physical grooves into it. These were the ones I was testing out last year. And it was before I ever got any self-induced, self-rotating ones. Before I learned how to put the magnetic fields into the magnets themselves, I was literally cutting slots. And it did shape the field. Just so y'all can see. You. So it does put like gear type waveforms. Both sides. There's very light, little tiny micro impressions. Now let's see what that looks like on here. The oscilloscope reset back to flatline, but let's see what this does. Wow. Now these lines are ground. I made a professional jig mounted on my lathe machine with to cut these with diamond blades at a specific angle, and it's still kind of all over the place. The electrical discharge actually is way better. But here's one rotation, one rotation. Let's just zoom in here and look at these things. Yeah, it's kind of all over the place. Wow. Not very good. It sure looks clean on the ring itself, but when you scan it with the oscilloscope, they're all over the place. All right, that's enough of that one. Let's move on to something better. Here's the one that rotates in relation to that spinning copper stator. The magnetic field has not just been placed on the face, it's actually on the up and down region. So it is actually going up and down, not just facial marks, which on these roller rings, you need to have both. You need to have one waveform that goes up and then goes back down on the other side. And then ultimately my goal is 136 tiny waveforms within that one big main carrier wave. So let's put this on. And then I'll let the oscilloscope reset. It is oscillating. I don't think I've even tested this to see what it looks like on the oscilloscope. So let's take a look and see what happens. Okay, that obviously was just the jolt. Wow. Wow. That is what I'm looking for. Look at this. My word. I've not seen this one yet. That's impressive. Very impressive. No wonder I'm having rotation. You see all the other ones, there was just these nice little squiggle marks. But look at that. Now, whoever goes on my Patreon account will be able to see how I did this kind of impressions on the magnetic lines and the wave fields. But let's move another step closer and look under some magnetic viewing film to see what this beautiful waveform looks like. So it's going like up, left to right. Come on, there we are. Almost reminds me of watching a snake move through the grounds or the water or smoke. Now to anyone's eye, this looks just like, oh, it's just waves. No, it's not just waves. These waves have to be in specific areas of this ring in order to get that rotation. Believe me, I've tried 20 to 25 different rings, and all of them were failures except for the final 4 when I did the pattern right, when I did the voltage right. And then you get this repeat, these nice harmonics. The pattern has to be just right. The voltage has to be just right. You can't just bump the waveforms all over. I was thinking it had to be one peak, one valley, which it is basically. So you have the full rotation. It looks like 2 peaks, 2 valleys. Yeah, 2 peaks, 2 valleys. And I tried one main peak, one main valley. It would not rotate in relation to the eddy currents produced from the stator. But this system seems to show 2 peaks, 2 peaks, 2 valleys, and then you get rotation. So let's do one more, and this will be the ceramic magnet I've done. Ceramic magnet, custom field. Kind of looks like a bicycle spoke, a lot like what John Searle talked about back in the day. Now this is just not a very good one. I had a good one, I'm not sure where it went to. I might have given it away. But you do have these nice spikes on here. This one had a little bit too much voltage on it. And this way it almost looks like knots. When I applied, this is pretty smooth, like that's pretty good here. But then you start getting this really just screwy field. So let's put it on here. See what this looks like. Okay. Now obviously this is far less power, far less dense, and things will be different on the scope. And this, I've tested these many times doing different techniques. I cannot get them to rotate in relation to a copper stator. They're really cool, but they don't do the what I call self-oscillation, so self-rotation. So here's the readout. And I will be watching the compasses to see if they deflect at all. That's better. It's pretty jagged. It is pretty jagged. But there's not really much uniform in this. In the fields. Wow, those lines are all over the place. Yeah, wow. Too much voltage on this one. It just fried the pattern. One rotation, the next. Okay, interesting. Let's move on. I have the 33 points, 1 empty. I forgot. I wanted to show you guys. This is the one I wanted to show you. 33 points and 1 empty. It's what John Searle told me in a dream. I said, oh, I got 34 points on this. He's like, that's really good, but you need one to be null. You need one to be null. So, the way he would say it. Let's put this on here and just watch the waveforms go by. Now, as I've said in the past, some of these do make these compasses deflect. And I don't remember which ring magnets it was, but I'm kind of curious now which one it was. Okay. All right. Let's watch these waveforms go.
Tomorrow, you'll see snowy, rainy weather.
Oh my gosh, you're killing me.
Expect a high of
Computer,
40 degrees Fahrenheit.
be quiet. Unreal. So many interruptions. Zoom in here a little bit. There we go. Let's take a look at this. Pretty uneven. Now this is an electrical discharge, of course, not cut in the magnet. There's basically one rotation and the next rotation. I believe what's happening is this is going negative. So let's flip this around. Not negative, yeah, negative, positive, north, south. That's what I'm thinking. So let's flip this around because I believe that null point should be going down, not up. Right, there we go. Reverse function. Let's watch this. Interesting, okay. So that is the null point. No, that's the null point. I thought that was. Let's read out this again. That's my null point. I'm not sure what that big spike is. Huh. Zoom out a little more to see what the full rotation looks like. And there's one rotation right through there. Interesting. So instead of going down like I thought it was, it must have peaked it. Okay, interesting. That's a cool one, but it's really dense in waveforms. Anyway, the goal is to get these things, like I showed on the first ring, is to get these waves so that they're just real uniform, not this kind of all over the place, which I've done. It takes a concentrated effort and realizing what works, what doesn't, and stick with that pattern. This is not, obviously not a perfected ring pattern. So let's move on to the next little bit I want to show you guys. Hold on. Sped this up to 13 RPM, and as it speeds up, the compass deflects. Yeah, definitely. I was just going too slow for it to be noticeable, but now it's going faster. Very cool. And that waveform. Choppy, choppy, choppy. All right. I've reviewed everything with the oscilloscope, the waveforms, the compasses, all that cool stuff. So this is moving into another category about resonance, mechanical resonance, the mechanical resonance of the system. I haven't yet delved quite into the electrical resonance of the system yet. That's to do with the magnetic waveforms, the charging of the Teflon parts. But for this, I wanted to shift focus into something that is very new to me. So I'll show you what I've got, and I don't have anything to prove out because it's still a work in progress. But there is some cool things to see. This little technique was something that I've seen and copied basically from Floyd Sweet, and I won't get into that series of topics, but it is another incredible inventor that had a parallel type of magnetization, a semi-parallel type of magnetization on his bar magnets. Similar to what Searle's doing, except Floyd Sweet was all basically garage, like this place. Garage-based, home-based. He would heat his magnets up in his toaster oven. He would wrap his buckets with wire, but he did some very phenomenal stuff. So I got the idea from Floyd Sweet to do this resonance chamber, mechanical resonance chamber. So I'm going to zoom the camera in here so you guys can see what I'm up to with this. Now inside this chamber, I have a coil. I've tried many different types of coils. Smaller coils, rectangle coils, all sorts of different type of size of wire, shapes, another custom one. And I always got about the same type of resonance points. Now the first attempt I tried was just a plain bar magnet, which is what Floyd Sweet would use, except his were like 4" by 6" barium ferrite. And I even have, so let's say, here's the bar magnet with a normal field. Very normal. Now I just play around with this, and this is a custom field, but it's very sloppy. So I'm not going to play around with these. But for intensive purposes, here is a normal ferrite, not barium ferrite, unfortunately, a normal ferrite ring magnet. So let's put it in this little chamber. And then what I found works really good for seeing oscillations, mechanical resonance points, is this tiny little X-Acto knife razor blade. I set it on there to find, basically finds the null point of the magnet. Let me zoom in a little bit. And then when you hit the right frequency with the right power level, which right now I'm running at about 1.7 volts with a audio amp hooked up to it, because this essentially is just a speaker. Coil of wire with a magnet near it. And at the right resonance points, the razor blade will start to flutter. So I'm set at 3 hertz and I'll increase it. Now I did a whole bunch of playing around with this before I started this video. Now here's 13 hertz. There we go, 13 hertz. I've been playing around with this for nearly about an hour, because this system is odd. It won't do anything for quite a long time, and then it starts to barely work, and then it starts to work better and better and better and better. Now there's no noise, but it is fluttering, you can see. No, that's not the camera either. So there have been points where I've been able to get this to flutter so fast it just falls off. And that's typically because too much power. And that's pretty good actually, 13 hertz. If I bring it down, 12 hertz, 11. Floyd Sweet, according to a few people who saw this, had self-oscillating magnets. Barium magnets that were self-oscillating, and with no power input, the magnets would do this kind of stuff to razor blades. My personal opinion is I think Searle had something similar to this too. Self-oscillating magnets. So there's 13, 14, 15, 16. So let's try 26. Maybe oop, no. There it goes. It doesn't like the high hertz. All right, little guy. Let's open you back up. Now, we saw what this responds to with this normal magnet. Let's try a magnet that has one of the patterns I put onto it. Now, this is not a perfect pattern. It's just a point of reference. I don't know if that's going to show very well. Oh, there we go. Sprocket look. So these do. Oh, I can feel that pumping. Come on. Stop this. Go back down. All right. Focus. The magnet orients itself differently. It almost looks like I'm looking at this and it's blurry inside because it's vibrating so fast. Come on, little guy. It behaves differently with these patterns on here. Yes, I want you to autofocus. There we go. Yes. Stay focused. Now, okay, that's a better way to see it. Now, I'm going to try keeping the power levels the same. There's 12 hertz. 13, 15 actually, 15 hertz. 16, 17, 18. So it affects the hertz rate. There's 19, 20, 22. Yeah, it's starting to move. Come on, stop. 21, 24, 18, 19, back it down, 17, 16, 14. Oh, no, that's 15. There's 14. Especially if the razor blade sits in between one of these gear teeth or on it around the waveform instead of just a solid blotch wall, it will mechanically make this resonate differently because of those wave patterns. Now, let's move on to doing a neodymium magnet. Now, this is, of course, one of my first trial runs, but this is a system I'm just beginning, I'm very new at. So it is not like this is the way to do it at all. I'm sure somebody could come up with a way better system. This is just my kind of playing around with these things. So this is what I've found so far that works well with neodymium magnets. Now, where is that one? Ah, here it is. Now here is a normal neodymium magnet, and what I did is attach magnets at top, and then here. Wait, stop it, stop it, stop it. Shut you off. Off. There we go, good. This is way more powerful. See how the magnets appear? And then I got this incredibly long and scary sewing needle. Okay, I just tested this out a little bit ago and it worked fine. There we go. There. So this holds the sewing needle in place, pinned to the magnet, and the field is holding it in place. I've tried this before with a razor blade, and because this thing is so short, the field is so strong, you can pump this all you want and that blade will be locked in space, do nothing. So I thought about it for a long time and did some trial runs, and the needle works pretty good. I wish I could see it better. There we go. That's a little bit better. See, the magnet's on top, holding it just to keep vertical. And then I'll play around with the frequencies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, wow. Okay, let's center it up. There, stop. Okay, 9 hertz. 10. Yeah, power levels are way different. So with this system, it's going to take a lot of fine tuning, a lot of working. And there we go, look at this, 8 hertz. So I tried this before I did filming, and it was 8 hertz. It seemed to move at 8 hertz pretty good, which is even lower. You know, it's a tighter, it's a more denser magnet. So as time goes on, I got a whole base for this, a whole setup. I'm gonna be playing around with it a lot more and developing like definite yes or no's, definite yes or no circumstances to find what works, what doesn't, play around with it, and develop some criteria for working with this system. Because it is fascinating to find mechanical resonance points with all this. So there's my sine wave generator. And I'm just using a standard sine wave, 1.7 volts, and I have a tiny little audio amplifier that's only 100 watts max, but it's way more than sufficient to run that. All right, that wraps it up for this video. I should have included this material in the first video, but I was like, what the heck, I'll just make a part 2. It'll be fun. So we've covered the oscilloscope readings, covered the gizmo to rotate, the ring magnets, the compasses, and then the different types of magnets I've been working on through the last several years. The copper stator and how it spins the magnets and what those wave fields look like on the oscilloscope, and then finally the resonance chamber. That one is still in the works. So if anybody out there wants to reach out to me for any reason at all, questions, comments, I have an email set up for this channel. It'll be in the description. And also head on over to my Patreon account. That is for serious people who are really interested in building SEG themselves and want to get the blueprints, schematics that I've created. That's on my Patreon account. I'm going to be making videos about all the cool details that I'm not showing here on this YouTube channel. But that's going to be covering exact sizes of the rollers, exact size of the stators, blueprints, like real good detailed blueprints with real actual sizes, schematics, weights, densities, the magnetizing process, and eventually down the road, the electrifying process to negatively charge the Teflon. So there's going to be a lot on that channel that I'm slowly adding to. Yeah, but next video is coming up soon, and just continue diving into this cool process, this whole project. And as I refine it, I'm going to be posting everything I can on YouTube, and the rest will all be on Patreon. Nothing is going to be hidden away. Nothing's going to be held in secret. I'm showing everything there is here on Patreon and on this YouTube channel, guys. So until then, I wish you well, and may God bless you in your efforts, and I'll talk to you on the next video. Woohoo! Faster! All right, one last thing I wanted to include in this video. This is going to be the bandsaw. I bought this about 15 years ago. Have fully rebuilt it in the last couple months, and this is going to be for cutting the rare earth discs for the rollers, and also for the stators, the arc segments for the stator pieces, stator 2 and 3. It's a beautiful setup. It's probably 20 years old, but I have fully renovated it. Water cutting, or coolant for cutting metals, because the thing with the rare earth, it is a pain in the butt. I've cut it and it sparks like mad. You can start fires. It'll start itself on fire. I know, I've tried. It's horrible for cutting. So you have to use a coolant system. You have to use liquid coolant, not water, but a coolant for cutting metal. So I'm hooking this one up. I might have to do an additional sprayer for the discs to cut them. But yeah, this is the next beautiful little project I'm completing. It's going to have a hydraulic downfeed control, and that'll be the next. So yeah, a little bit behind the scenes of what's going on. This is what I've been on for like the last 2 months, getting this finished up, and it's almost done. So you'll see me working as future videos come along, working on the rare earth. But I have to get high performance tools that work really well for what I'm doing. And rare earth is nothing to play around with, nothing to mess with. It will burn like mad. And so this system will allow it to cut smoothly and not be starting fires or melting the blade. Anyway, that's it for the video. I'll catch you on the next one. Take care.